Today in this video we are going to discuss about radial and cross radial components of velocity and acceleration. This is a polar frame of reference. We all know that in polar frame of reference we only have an initial line OX with origin O. This type of polar coordinates are used to understand and evaluate the different concepts in astronomy. Actually, Kepler's laws of planetary orbit are basically dependent on this polar frame of reference framework and the radial and cross radial components of velocity and acceleration. So in this video, let us try to understand about the method of calculating the components of velocity along velocity component along radius vector. So in this diagram, let us take a look at the diagram pensively. Let us take a look at the diagram. I think it is visible clearly. Let us pensively look at this diagram. This is a point P having coordinate r and theta. So OP is the radius vector r. OP is the radius vector r, and theta is its angular elevation with respect to this initial line OX. So this point traverses along this curve and reaches P prime within a time delta t. The points P and P prime are infinitesimally close to each other. So it spans from P to P prime along the curve in a time delta t, obviously, which is a very small quantity. Isn't it so? So P and P prime are very close to each other, and in this diagram I have intentionally drawn the PP prime chord with a green ink. This one is red, the original radius vector OP, which shifted to P prime. OP prime is the new radius vector having r plus delta theta plus delta theta as the coordinates. So this POP prime angle is nothing but delta theta, isn't it so? POP prime is delta theta, marked in this figure diagram. I hope you can easily see this. So this is the scenario. The point traverses from P to P prime along the curve drawn in black ink, and the green ink denotes the chord PP prime, which is actually merging to the tangent drawn at P. Now we just extend this radius vector P to L and drop a perpendicular P prime L on OPL. So this angle OLP prime is right angle. OLP prime is right angle. And so what is the velocity component along the radius vector OP? Obviously the velocity component is rate of change of displacement. Isn't it so? We all know that the rate of change of displacement is the velocity. So rate of change of displacement along the radius, along OP. So it's obviously we extended OP to L and dropped a perpendicular from P prime. So what is the distance it traversed along? It traversed along the curve from P to P prime. So it traverses a distance PL along the radius, isn't it so? The extended radius vector OP meets the perpendicular dropped from P prime at L. So PL is the amount of displacement along the radius. I hope you all can understand from the geometry of the figure. Along OP, the displacement is PL when the point traverses along the curve from P to P prime. And what is PL? PL is nothing but OL minus OP. What is OP? OP is written as R. And what is OL? Since OP prime is R plus delta, we can easily see from the coordinates. So OP prime is r plus delta r. And this angle is 90 degree. I have written it. And this angle is delta theta. So obviously the OL will have a length. OL, actually PL is nothing but OL minus OP, and OP is actually R, and OL is nothing but R plus delta R cos delta theta. It is nothing but, I just wanted to shift it a bit lower. So this becomes R plus delta R cos delta theta minus R by delta t. Now as delta t tends to 0, delta theta also tends to 0, and whenever delta theta tends to 0, then we all know that cos delta theta tends to 1. Isn't it so? Whenever delta theta tends to 0, we must have cos delta theta tends to 1. So this becomes 1. And when this becomes 1, this r and r cancels out, and it is delta r by delta t. And when you take the limit, this is nothing but dr dt. So this is the component of velocity along the radius, or we termed it as a radial velocity. Clear up to this point? Now let us move on to find from this figure let us move on to find from this figure what is the velocity component along the perpendicular direction of the radius. What is the velocity component along the cross radial direction? Isn't it so? Radial and cross radial. What is cross radial? Cross radial is along the perpendicular velocity component along the perpendicular direction of the radius. Perpendicular direction of OP. So what is the perpendicular direction of OP? P prime L. And precisely P prime L is the displacement along the perpendicular direction of OP. So the velocity component will be P prime L by delta t. Isn't it so? Rate of change of displacement along the perpendicular direction of OP. So as P traverses along the curve from P to P prime in time delta t, which is infinitesimally small, we should take the limit as delta t tends to 0 of P prime L by delta t, because that is the rate of change of displacement along the perpendicular direction of the radius. It is quite clear from the figure. It is also quite clear from the figure that P prime L will be the perpendicular of the triangle OP prime L, of which this is a 90 degree, this is a right angle triangle, and this angle is delta theta. So obviously this is r plus delta r sine delta theta. Isn't it so? P prime L is nothing but, since hypotenuse is r plus delta r, which is OP prime, so P prime L is the perpendicular, and it will be r plus delta r sine delta theta by delta t. Clear? And with similar logic, as delta t tends to 0, delta theta also tends to 0, and we have sine delta theta tending to delta theta. Isn't it so? Sine delta theta always tends to delta theta, as delta theta tends to 0. We all know that sine delta theta by delta theta actually tends to 1. So sine delta theta tends to delta theta. And what is this? This is nothing but r plus delta r into delta theta by delta t. And obviously we are going to ignore the quantity delta r into delta theta in comparison with r into delta theta. Quite logical, because delta r into delta theta is much less than r into delta theta. So whenever you add these two quantity up, we are left with only the first one. We can easily ignore the second one. So we replace it by r delta theta by delta t. The logic is quite clear. Isn't it so? Here it is r plus delta into delta theta by delta t. Delta r into delta theta is much smaller in comparison with r delta theta. So we ignore it and we take the limit of r delta theta by delta t. As delta t tends to 0, this turns out to be r theta dot or r d theta dt. And that is what is precisely called cross radial velocity. Component of cross radial velocity. Okay. Now let us move on to find the components of radial and cross radial acceleration in a separate video.